So let's say we have this linked list of free nodes, and now we have to find a good way of searching that list of free nodes and returning one of them for that will fit a request. The one that we will look at first is called first fit. And so the idea is really simple, is that you write a loop to scan that linked list, and then as you search in that list, you're going to return the first node that will fit the request. Doesn't matter how big it is. Just if it fits, return it. The nice thing about something like a strategy like this is it's fast because you may not have to search the entire list. You might, the very first node in your linked list might be big enough. However, so even though this is fast, there's a problem. The problem is that you may end up with a lot of small nodes. Once you get hundreds of requests, you might end up with, since you're going to return like the first thing that you find that's going to satisfy the request, you're going to end up with a lot of small nodes at the beginning of the free list. That's going to be a big problem. And there are some things that you could do. For example, we'll take another look at another version of this, but if the allocator uses an ordering of the linked list based on the address, so lower address is first and higher address is last, then coalescing is actually not so bad. You won't have a hard time coalescing because they're all in order, and so you can just check um, adjacent nodes in the free list and check and see if they're free and they're adjacent, then you can coalesce them pretty easily. Okay, so there are advantages. It's fast. You can use coalescing would be easy, but you could end up with a lot of small nodes at the beginning of the list. Another strategy for allocating is next fit. So the idea is pretty much the same as the free list, except that you keep a pointer to the node in the free list that the last good node was found. So whatever you allocated from, you take out some chunk and then you put the remaining back into the free list, and then you start searching at that point where you left off with the last malloc, essentially. So search the free list starting from this pointer that was the result of basically the result of the last malloc, and then return the next good fit. This is also fast because you're maybe pointing to the thing that's probably the most likely to fit anyway. And the thing is, you may also fix the problem of having many fragments at the beginning because you're going to allocate from where you left off. So it's not always going to be, in the beginning that you allocate the fragments from, or allocate the request from. Okay. Another strategy is to use best fit. So with best fit, you have a linked list and you have to search the entire free list and then find the best match. Of course, if you find an exact match, let's say you have a free list somewhere in the middle, you have a chunk of memory that's 100 bytes and you get a request for exactly 100 bytes, then of course you found an exact match. You won't find anything better, so you stop searching. But that's not always that likely, and so typically you'll have to search on the worst case. Typically it'll be the worst case, I guess, which is that you have to scan the entire list, and then you keep track of the smallest one that fits the request, and then you return that. Problem with this is if you get many requests, after millions of requests, you may end up getting a lot of very small fragments because you're always trying to find a really good fit, and even though the name sounds like, oh yeah, that should work, but no, you'll probably end up with very small fragments that are completely unusable, and then a lot of them. That's the danger. Last one we look at, or actually one of the second last ones we look at, is called worst fit. The name of it actually sounds not so great, but the idea is to find the largest chunk and then split it. And it turns out this can be the solution to the problem of best fit. That is, in best fit you end up with a lot of little tiny fragments left over, and that's many of them. Worst fit may fix those because it'll take the biggest chunk and then split that, and now you have the biggest chunk left over. You don't have small chunks left over, you have big chunks. So it turns out that does work sometimes. So here's an example. Suppose we start with this linked list, uh, 3 nodes in the free list. So you have a chunk of memory that's, let's say, it starts at 10, or let's say these are just the sizes, so 10 units of space, 30 units of space, and 20 units of space. This doesn't tell you where the address is, it's not important. And then let's say we get a request for 15 units of space. So if you use best fit, you would say 10 is not big enough, 30 is big enough, but let's look for a better fit. And so you would find the 20, and then you would allocate 15 out of the 20, leaving us with this small chunk in this case. Worst fit, if you start with this and you get a request for 15, you would say 10, that's not big enough. 30, well, yeah, that could work. And then you'd keep going and you look at 20, well, that would fit too, but then this is a worst fit, and so I'll use this in worst fit. So you end up with a chunk of size 15 in the middle. So if you take a look at these, you can just you can't really see a pattern after just one request, but you can see you end up with a small chunk here, whereas these are all roughly the same size. So you can see the trend after many requests. You'll see that in probably you'll end up with worst fit with a lot of medium-sized chunks. Maybe best fit could end up with a lot of small unusable chunks of free space. Okay, another kind of allocation scheme that is actually used in Linux is called buddy allocation. And the idea behind this is that it's very simple if you use blocks that are of size power of 2, some power of 2. And so there is a restriction. No matter what your request is, you're going to allocate block sizes that have to be of size power of 2, some power of 2. So the allocation strategy, if you get a k byte request, is you find the nearest power of 2 that's bigger than the k. So you raise, essentially what you do is you raise the allocation request to the nearest power of 2 that's bigger than k, or bigger or equal to. And then you search the free list. If you don't find a perfect free node that's exactly the size that you're looking for, power of 2, then you take some large block and then divide it recursively until you find the correct size, 2 to the m. And then what you'll end up with is there'll be a buddy block right next to it, which will be free, and so which is not used, that is. And then when you call, so this is for malloc, and then when you call free, you will have, maybe potentially free buddy nodes right next to you that you can coalesce easily. So the whole idea of buddy allocation is, sure, you might be allocating chunks of memory that's bigger than you need, but you might be able to coalesce very easily and very quickly, and maybe make best use of memory. So as far as the question of which of these allocators is best, it depends completely on use. What kinds of requests are going to come in? If you knew what's going to come in the future, of course, you can plan it out and figure out the best scheme. So you cannot predict the future, and so the bottom line is all of these might work for some, and any one of these might work for some situation. Okay, so there are also slab allocation schemes that try to pre-allocate and pre-initialize chunks based on the past usage. So the idea there is this is something that you see in computer science a lot. If you see a pattern of use in the past, and you can guess that the near future will look like that, and so you sort of take You sort of try to be proactive and say, okay, I used chunks of size 100 in the past. It's likely that I'm going to get the same kinds of requests, and then you can pre-initialize these 100 byte chunks, assuming that you're going to get more of those. Okay. So if you take a look at these allocators that we talked about, best fit, first fit, worst fit, and buddy, if you compare them, best fit, remember, we'll end up scanning the entire linked list, and so that might be slow. So it's called an exhaustive search. You search all the nodes in the free list. If you have a million nodes, and that's going to be slow. In actual practice, what tends to happen is that you tend to leave very large holes in best fit or very small ones. And so the very small ones is what leads to what's called fragmentation, because you have very small ones. They may not be usable, but if you were somehow able to coalesce them, it would be usable, but coalescing may not be easy. First fit, on the other hand, we saw that it's going to be fast because you just take the first node, and so you'll end up with nodes in the front of the list that are maybe small. In actual practice, it tends to actually leave average size holes, so it's not so bad. Worst fit, actually, we thought maybe it's not such a bad thing compared to best fit, but it also actually tends to fragment just like best fit, and it has the same overhead as best fit because you have to scan the entire list. So if there's a million nodes in your free list, best fit is slow, worst fit will also be slow because of that high overhead. With buddy allocation, what you'll get is allocating powers of 2. So for example, if you get a request for 1023 units of space, the nearest power of 2 will be 2 to the 11, which is 2048, which means most or about half of that chunk of memory is unused. So that's worst case scenario. So you could get what's called internal fragmentation. You get a big chunk of memory out of which you're using just a little over a half. So that's always possible. So in the real world, what does malloc use? So if you call the C malloc function in a program, what it really does is it calls this function sbrk, which is like memory map. It says, I'm going to increase the amount of virtual memory that I'm using. I'm going to create a new node of memory, and so it's going to request more of this contiguous memory, virtual memory, from the operating system, and then malloc will add a small header to each block of memory with the pointer to the next free block, the size of the current block, and so on, as we saw in that linked list. And then it will keep a separate free list for each popular size, so that if you get a request for one of the popular sizes, that allocation is going to be fast. And then also you can avoid fragmentation. However, this can be inefficient. It might not actually use any of that memory. It might end up sticking around. And typically, depends on the implementation, but you will tend to use something like first fit for the free list of irregular block sizes. So it'll use like a mix of strategies, not just one strategy in real world malloc implementations.